When you first dive into game development, you probably start by downloading a game engine and following a few tutorials to learn the basics. When you have a minimum understanding of the engine interface and how the scripting language works, many of us end up trying to create a simple 2D platformer to practice what we just learned. At first, it seems straightforward. You want your character to stand still, run, crouch, jump, pick objects, climb stairs, and so on. But as you keep adding features, the script that controls your character grows longer and more complicated. Before long, you realize just how challenging it is to manage all these character states in a single script. Now, imagine you decide to take that 2D platformer from a small learning project to a full-fledged game. Suddenly, you're adding even more mechanics. Double jumps, wall sliding, swimming, flying, various attack types. The list keeps growing. Without a solid way to manage all these states, you will end up with a script with hundreds of lines, which is a nightmare to modify or debug. The classical solution to this problem is the use of finite state machines, which are essentially a practical implementation of this state pattern. The state pattern is a programming design pattern that involves encapsulating individual states of an entity, often as separate classes. Each state handles its own behavior and logic, and the finite state machine manages these states, ensuring that only one is active at any given time and allowing seamless transitions between them. For example, in our 2D platformer, when the character is running, it will be in the running state. If the character jumps, it transitions to the jumping state, and so on. The finite state machine ensures these transitions happen in an organized and controlled way, avoiding messy or conflicting behaviors. I know there are plenty of tutorials on YouTube about finite state machines. However, in this video, I aim to go beyond the basics and teach you how to implement one using the fundamental principles of good architecture. In essence, what we will be focused on is leveraging the state pattern to create a robust and maintainable system that makes managing game states much easier. If you're interested in diving deeper into the state pattern, finite state machines, and other patterns, I highly recommend the fantastic book Game Programming Patterns. You will find a link to the free online version in the description of this video. If, like me, you prefer the feel of a physical book, I've also included a purchase link below. It's a great way to support the author and this channel while exploring a variety of software design patterns tailored for game development. And now, without further ado, let's see how we can use the state pattern to create a finite state machine in Godot. To get started, I have prepared a project where we will give this character the ability to run and jump. I've also created a map with proper collisions to serve as our testing ground. In this tutorial, we're going to focus entirely on programming the state machine. I won't be covering how to implement animations, create the map, or anything like that. I will assume you're already familiar with those basics and that your main interest is in learning how to apply the state pattern. Additionally, I've included a link to the source code for this project in the video description, so you can explore it more closely. However, please note that I don't have the right to redistribute the assets used in the project. This means that if you download it, you won't be able to run it as the graphic resources will be missing. That said, you will still have full access to the scripts we're going to write in this video. The first step we need to take to create our finite state machine is to define how we are going to encapsulate our states. There are several ways to do this. For example, states could be encapsulated as simple functions within a script. However, in this video, we're going to use a more classic approach by encapsulating each state within its own class. This gives us much greater flexibility and allows each state to have its own unique capabilities. I will start by creating a new script in the base directory and naming it state.gd. In this script, we will define the methods that every state will use. The first method is called enter. This method is like the entry point for a state. It will be called whenever the state machine transitions to this state. and it's where we can initialize variables or perform setup actions specific to that state. Next, we define the exit method. This will handle everything that needs to happen when leaving a state, like releasing resources or cleaning up before transitioning to the next state. We also need methods for updating the state. The first one, process, will run during Godot's process event, which is called every frame. The second, physics process, will run during Godot's physics process event, which is synced with the physics engine. These two methods are where we will write the frame-by-frame behavior of each state. This gives us the basic structure of a state. Each state will inherit from this state class and override these methods to define its specific behavior. Next, we're going to create another class that will serve as the state machine. This will be responsible for managing all these states, transitioning between them and ensuring that only one state is active at any given time. Let's create a new script called statemachine.gd in the base directory. Once it's created, delete everything inside and set the class name to stateMachine. For this script, we're going to inherit from node, because the state machine will be attached to a node in the scene tree. The first thing we need to define is the current state variable. This will keep track of the active state currently loaded in the machine. After that, we also need a way to store all the available states so the machine can transition between them as needed. Next, we need to initialize the state machine. To do this, we will create a method called startMachine. This method will take the list of available states as its input and set everything up. Inside this method, we will store the input states in a new variable called states. But here is where we encounter a problem. We need a reliable way to identify each state by name. To solve this, we will go back to the state class and add a new method that returns the name of the state. If a child script doesn't override this method, it will throw an error. This ensures every state has a unique name, making it easier to identify and work with. With this naming system in place, we can now organize the states into a dictionary where each state is stored under its corresponding name. After that, we will initialize current state to the first state in the list. There are other ways to determine the initial state, but to keep things simple for now, we will just use the first one. Finally, we need to activate this initial state. To do that, we call its enter method. At this point, the state machine is running, and the first state is fully initialized and ready to go. Next, we need to define the process and physics process methods. These are straightforward. Our job here is simple to call the corresponding methods of the active state. This ensures that the current state's logic runs every frame as expected. To finish the state machine script, we need a method to handle transitions between states. I will call this method transition, and it will take the name of the target state as its parameter. Inside this method, the first step is to try to retrieve the instance of the new state. To help with clarity, I'm also going to define a helper variable to store the name of the current state. The first thing we need to check is whether the new state is valid. It's possible someone might try to transition to a state that doesn't exist. If that happens, we will throw an error to catch the issue early. Next, we need to check if the new state is different from the current one. If it's the same, there's no need to transition, so we will throw a warning to indicate the unnecessary request. Now we can perform the actual transition. To do this, we first call the exit method of the current state to clean up anything it needs. Then we update the current state variable to reference the new state. Finally, we call the enter method on the new state to initialize it properly. And that's it. With this, we now have a basic finite state machine script ready to handle transitions and manage states in an organized and efficient way. Next, we are going to attach the state machine to the main character. To do this, I will create a basic node in the player scene and attach the script we just wrote to it. Now I will create a new script to control the main character. I will place it in the source folder under player and name it playercontroller.gd. For now, I will keep this script simple and only include references to the nodes we need within the states. For example, I will add a reference to the animation player node that's already set up in the character. This node contains animations we will use later. I will also include references to the state machine itself and the sprite 2D node. At this point, I will define the ready method, but we will leave it empty for now. We'll come back to it later. Now, pay close attention, because what I'm about to do is a little trick to make working with this stage much easier. Think about it. In each state, we will often need to access the same elements, like the animation player, the sprite 2D, or even the state machine. Instead of repeatedly writing code to access these elements, we're going to make the process more efficient and flexible. To do this, I will create an intermediate class called playerState. This class will inherit from state, the one we created earlier. Inside playerState, I will define variables for all those commonly used elements, like the animation player and sprite 2D, that we will need to work with in our states. In the constructor for playerState, I will pass an instance of the player controller script. Using this instance, I will initialize all these variables. This way, whenever we define new states for the character, those states will inherit from playerState instead of state directly. By doing this, we can quickly and easily access these variables within any state. You will see in just a moment how this approach makes our code cleaner and more efficient. Now, let's start defining the different states of the character. We will begin with the idle state. I'm going to create a class called playerIdleState, which, as I just explained, will inherit from playerState. And since playerState itself inherits from state, we are building on everything we have created so far. In this class, I will define a static variable to store the name of the state. I will also implement the getStateName method to return its name. This ensures the state machine can accurately identify the idle state when transitioning between states. Next, let's define the movement state, which I will call playerMovementState. Since the idle and movement states are closely related, it makes sense to create them both at the same time. In the movement state, I will begin by adding some variables specific to character movement, like acceleration and maximum speed. Let's pause here for a moment to highlight one of the biggest advantages of the state pattern. By encapsulating all the logic and behavior related to movement within this state, we avoid the mess of having hundreds of unrelated constants cluttering up a single character controller script. Instead, the logic is self-contained and easier to manage, making the rest of our code much cleaner and more understandable. Now let's add the logic for the character movement. To do that, the first thing we need is the user's input, like which movement keys they're pressing or which direction they're moving the joystick. While it's tempting to handle this input directly in the movement state, it's not the best approach. That's because input isn't exclusive to the movement state. Other states may need it too. This is something you will encounter often when working with the state pattern and finite state machines. While encapsulating logic within states is great, sometimes you will also need shared variables or functions that multiple states can access. To handle this, I'm going to go back to the player controller script and define a variable called horizontal input. This will store a float value representing the character's horizontal movement input. I will populate this variable in the physics process method of the player controller. Now, back in the movement state, I can use the horizontal input value to write the movement algorithm. Here's how it works. I multiply the user's input by the character's acceleration. Add that value to the x-axis of the character's velocity. and then use the clamp function to ensure the character's speed doesn't exceed the maximum allowed value. Since this tutorial is focused on the state pattern and finite state machines, I won't dive too deeply into the movement algorithm itself. The important takeaway is how we're using the state pattern to isolate movement logic, keeping the codebase clean and easy to extend. Now, let's go back to the player controller script. In the ready function, we're going to create an array containing instances of all the states we want to provide to the state machine. Since these states inherit from player state, they need the player controller instance in their constructor. That's why I'm passing self when creating each state. Once the array is ready, we initialize the state machine by calling its startMachine method and passing in the states we just created. Now I will run the game and press the movement keys, but nothing happens. This is a bit of a debugging issue because, without any feedback, we don't know what's going wrong. To make troubleshooting easier, let's add a login system to the state machine so we can see what it's doing. Back in the state machine script, I'm going to add an exported variable to enable or disable logging. For now, we will log when a state starts and when it stops. To do this, I will add a variable to store a reference to the name of the parent node. This will make the logs more informative. I will also add login in the transition method so we can see when transitions occur and which states are entering or exiting. With that done, all we need to do is activate logging in the editor on the state machine node. Let's run the game again. Now we can see in the logs that the state machine correctly starts in the idle state. However, nothing else happens yet. This is because we have programmed the movement logic in player movement state, but we haven't told the state machine when to transition between the idle and movement states. Let's fix this. In the player idle state, I will add a check to see if there's user input. If there is, the state machine will transition to the movement state. I will run the game again and press the movement keys. Still, nothing happens visually, but now we can see in the logs that the state machine is transitioning correctly to the movement state. We're making progress, step by step. Let's go back to the player controller script. If we take a closer look at the physics process method, we will notice that we have left out a critical detail, the call to move and slide. At first, you might think it makes sense to call this method directly from the states. However, this presents a problem. The movement logic is something that needs to happen every frame, regardless of the character's current state. This makes it a perfect candidate for centralization in the player controller. By keeping the move and slide call in the player controller, we ensure that it's consistently executed every frame, without tying it to any specific state. This approach keeps the behavior predictable and avoids unnecessary duplication of logic across multiple states. Now I'm going to run the game, and I can see that I'm able to move the character. However, there's an issue. Even though you can see it, I'm releasing the movement key, but the character keeps moving indefinitely. This is expected because we haven't programmed the logic to transition from the movement state back to the idle state. Let's fix that. In the player movement state, I will add a condition to transition to the idle state when no input from the player is detected. While I'm here, I will also take care of setting the correct animation. Since animations are independent on the engine's physics, this logic should go in the process method. I will do the same for the idle state to keep everything consistent. I will run the game again, and now the animation looks better, although we have a couple of new problems. The first is that the character always faces the same direction, and the second is that even when the character transitions to the idle state, it keeps moving instead of stopping. The reason for this continuous movement is simple. We haven't programmed any kind of deceleration to stop the movement smoothly. Let's fix that in the idle state. I will define a stopping force and apply it to the movement vector on each frame. This will allow the player to come to a stop with a bit of smoothness. I will run the game one more time, and now the movement works as expected. Now let's address the problem of the character always facing the same direction. Since this action will be needed in multiple states, it makes sense to centralize it in the player controller. First, I will create an enum to define a list of possible facings, such as left and right. I will also add a variable to keep track of the current facing. Then I will define a method to handle turning the character to the correct side. To do this, I will use the horizontal input variable as a reference. Based on the direction of the input, the method will adjust the sprite to ensure the character is facing the right way. With that done, we need to call this method in both the idle state and the movement state to adjust the character's facing on each frame. Now I will run the game, and we can see that everything works as it should. The character's movement, animation, and facing are now all correct. So far, we've gone into quite a bit of detail on how to create a finite state machine using the state pattern to manage the states of our game's character. To wrap up this tutorial, we're going to add one more state, the jump state. This will allow us to explore a few additional details that are worth discussing. To start, I will create a new script called player jump state, which, like the other states, will inherit from player state. I will identify it with a unique name, just as we've done before, and then add some variables specific to jumping. This includes the jump force, the maximum force, horizontal acceleration, and speed while in the air, and a stopping force to manage movement in the jump. We will also need to track whether the character is actively jumping, and we'll use a variable for that. At this point, you might be wondering, if we are in the jump state, doesn't that automatically mean the character is jumping? Well, not exactly. When you press the jump button while the character is on the ground, the state transitions to the jump state, but the character isn't actually airborne yet. This is why we need this variable, and you will see shortly how it becomes essential for handling this state correctly. First, let's handle the horizontal movement, which is also necessary in the jump state. I will take the user input and apply it to the movement vector. This logic is very similar to what we already have in the movement state, but with a key difference. The variables controlling horizontal movement in the air have different values compared to when the character is on the ground. This allows us to give the character distinct physics while airborne. Next, we need to make the character take off from the ground. This will be handled in the enter method. Here, we will first verify that the character is on the ground, and if so, apply a vertical push force to make it jump. Similarly, in the exit method, we will set the isJumping variable to false, as the character should be touching the ground by the time this state ends. Now let's add the logic for transitioning into the jump state. This will be done in the process method of both the idle and movement states. Once that is ready, we will also add this new jump state to the states array in the player controller, so the state machine can properly manage it. I will run the game now and I see that the character can jump, but indefinitely. To fix this, we need to apply gravity to the character. Since gravity needs to be applied consistently, regardless of the current state, it makes sense to centralize this in the player controller. I will define a variable to retrieve the gravity value from the project settings and apply it in the physics update method whenever the character is not on the ground. Alright, now the character can jump and return to the ground, properly affected by gravity. However, if we check the logs, we can see that the character remains in the jump state even after landing. This happens because we haven't added logic to transition back to the idle or movement states once the jump is complete. Let's fix that in the physics process method. Here, we will detect if the character is on the ground. If our control variable indicates that the character was jumping, meaning it has just landed after a jump, we will check the user input to decide whether to transition to the idle or movement state. Now the character can jump and move freely, with the state machine correctly transitioning between the available states. Let's move on to fixing the jump animation. In this case, we have two animations, one for when the character is going up and another for when it's coming down. I will add a constant to represent a minimum velocity threshold to help us detect whether the character is ascending or descending. Depending on the direction, we will play the corresponding animation, and of course, we will also update the character's facing during this process. I will run the game now and everything looks much better. The animations, movement and transitions all feel smoother. However, there's still one issue. Watch this. If I let the character fall off a ledge without pressing the jump button, it doesn't transition to the jump state. This is because we have only programmed the transition to the jump state to happen when the jump button is pressed. In this case, though, the character should still transition to the jump state, because this is the state responsible for managing aerial movement. Let's address this issue in the player controller, specifically in the part of the code where gravity is applied to the character. We'll add a check to ensure the state machine transitions into the jump state when the character is falling off a ledge. With this adjustment, if the character moves off a ledge and falls, it now correctly transitions into the jump state, ensuring that the aerial movement logic is applied as expected. This wraps up our tutorial on the state pattern and its common use in game development for creating finite state machines. Another powerful pattern you can apply in Godot is the singleton pattern, which Godot implements using its autoload feature. If you're interested in learning more about this pattern, click on the video you see on the screen. If you found this video helpful, please give it a like and consider subscribing to the channel for more content like this. I hope you have a beautiful rest of your day. Goodbye.